We're going to be covering primate locomotion. So there are several categories of locomotion we're going to be looking at. One is vertical clinging and leaping, and this is usually associated with strepsirrhines, but there's one primate that kind of looks like a strepsirrhine, but it's not. And so the tarsier is also a vertical clinger and leaper. So mostly strepsirrhines, but with the exception of the tarsier. And then we're going to be looking at different forms of quadrupedalism and suspensory. And then we've got bipedalism. And today, we are the only bipeds left in the primate world, but when we get to human evolution, you'll see a whole load of other species that were able to walk bipedally habitually. So vertical clinging and leaping has some interesting traits that are associated with it. They have these really long, powerful hind legs. That's because of the way vertical clinging and leaping moves. Yet they have to really push off from the tree. So their hind legs are actually longer than their forelegs, which is something we don't usually see with the exception of humans. Humans have longer legs and arms, and most other primates either have equal lengths of arms and legs or longer arms and legs. Their body posture is often vertical. They usually aren't on horizontal like a monkey or an ape. And so they have an interesting foramen magnum as well. They have long grasping hands and feet to hold onto those trees, and they're incredibly powerful because if you think you have to jump, essentially leaping from one tree to the next, you're not swinging, you're leaping. So you've got to have some really powerful hands and feet.
And the difference between tarsiers and other vertical clingers and leapers such as lemurs is that the tarsier has an extreme elongation of the tarsal bones, even more so than other vertical clinger and leapers. And this enables the tarsier to have a very different mechanism of foot rotation so that it can grasp these vertical stems with an inverted foot.
And then the foramen magnum, which is part where the spine meets the skull. So it's the hole underneath your head where your vertebral column goes in, right? Where your atlas meets your occipital condyles. We use the placement of the foramen magnum to try to figure out locomotion. And this is one of the most challenging aspects of this particular part of Unit 3. Students really struggle with trying to figure out where the foramen magnum is and what it says about the primate, especially on our cast materials. So I think you guys are kind of lucky in this respect because I tried to pick pictures that were quite obvious in terms of the placement of the foramen magnum. So there's 3 different positions that the foramen magnum can be in. There's an anterior position. The anterior position is really inferiorly anterior. So it's underneath the skull, but it's more towards the face. The centralized position is underneath the skull, but it's more kind of in between the posterior and anterior position. And then there's the posterior position, which is on the back of the skull. And that's what we see for most quadrupeds. For bipeds, we see a centralized or anterior position of the foramen magnum, but we also see it with vertical clingers and leapers. So if it's centralized, it could be a hominin, it could be a biped, an intermediate biped, but if it's centralized and it's super small head, it could be a vertical clinger and leaper. So you have to remember that vertical clingers and leapers show traits that are associated with bipedalism. But, obviously, if you look at a skeleton of a vertical clinger and leaper, you're going to be able to tell that it's not a biped, even though it has these positions and intermembral indexes as the same as bipeds.
What's an intermembral index, you ask? It's a number that we get from putting in particular measurements from a primate of their bones into a formula. And so this mathematical equation right here, humerus length plus radius length over femur length plus tibia length multiplied by 100, this gives you your intermembral index. And then the chart below shows you what numbers correspond to what locomotion patterns. But as you can see, for the first range of numbers, 50 to 80, it can be both a bipedal organism or a vertical clinger and leaper. VCL stands for vertical clinger and leaper. And so it's really easy to tell what a primate is doing as they are alive in the trees or on the ground, but it's another thing to look at bones and be able to tell what kind of locomotion pattern they practice primarily. And this is why we use the intermembral index. So when you're looking at a biped versus a vertical clinger and leaper, you can tell the difference right away. But you're going to need to know specifically what part of the body can you point to that differentiates vertical clingers and leapers from bipeds, because a lot of the traits are similar. In addition, if you get an intermembral index
between 80 and 100,
you're going to have to decide based on looking at the primate whether or not they're just what type of quadrupedal they are, or whether they're semi-brachiators, for example. So you'll have to use both the number that you are provided, and it's really hard to measure online, so I'm not going to make you actually measure the different bones, but I will give you intermembral index numbers on the exam, and you're going to have to figure out what locomotion pattern that number will give you, but also based on the pictures, what do they look like they do?
So vertical clinger and leapers, they have, this is just a summary of them, they have longer legs and arms, their centralized position of the frame and magnum, they have vertical posture, all these things they share with bipeds. And they even, as I said, they even have the same index, but they're not bipeds, they're vertical clingers and leapers. And if you're thinking about what trait would give it away that the tarsier here is not a biped, is actually a vertical clinger and leaper. Tarsiers have elongated tarsals. This right here is actually their ankle bone, and compare it to our ankle bone, right? So this is their ankle bone and this is our ankle bone.
So another trait you can analyze to determine whether you are looking at a vertical clinger and leaper or a biped is the pelvis. And so
our pelvis is bowl-shaped and the tarsier or the vertical clinger and leapers aren't. In addition, they have tails. So whenever you see a tail, you know for sure that's definitely not a biped, and even still, definitely not an ape.
And although this doesn't look like a tail, it's still considered a tail because it's a longer coccyx than our own.
So curvature of the column also. So if you see this curvature, you know that's not a biped because bipeds have an S-shaped spine. So I want to show you the clip
Of a type of lemur doing vertical clinging and leaping.
Clambering about here requires some very delicate footwork indeed. Mother's tail clearly makes a better handhold for a youngster, but even at this age, a young shifak is able to negotiate the spines. Collecting dideria leaves and flowers, and they're the shifak's main food, looks even more hazardous than travelling around through its branches. But when shifaks decide to move, they can travel very fast indeed. They use the same basic method as bush babies, but do so with such speed and confidence that they seem almost to bounce from trunk to trunk. Only in slow motion can you see just how accurately they land and how instantaneously they're able to take off again. But given the chance, they assess their jumps with care. Takeoff has to start sideways on to the line of flight, so they have to rotate their bodies in midair. Then those hind legs, having kicked off, have to be swung forward to act as shock absorbers as they make contact. Their back feet are long and narrow with an enormous big toe so that they can lock onto a trunk as soon as they hit it. Then, within seconds, they're off again. And a female can even do all this while she's carrying a baby. Down on the ground, however, the method doesn't work quite so well. Extremely long legs and very short arms make it impossible to run on all fours, so once again it has to be jumping. But with no vertical trunk to push away from, the leaps are rather shorter. Back in the trees, they can travel at speed again. And they need to, for they have a savage enemy. The fossa. Its speed through the branches rivals that of the shifaks, but its technique is entirely different, for it's not a primate with jumping ancestors, but a kind of giant mongoose, and it's still a four-footed runner. Nonetheless, they're a close match for one another. But when it comes to the long jump, the shifak wins. A four-footed runner can't match that.
Now we're going to look at the branch of locomotion called quadrupedalism, which means walking on all fours. There are many different kinds of quadrupedalism. There's quadrupedalism that's only in the trees. There's quadrupedalism with a fifth hand. There's a prehensile tail. There's quadrupedalism that only happens on the ground. And there's knuckle walking and fist walking and all different types. So we're going to be looking at all of these. So arboreal quadrupedalism, they usually have relatively equal lengths of arms and legs. They usually have a really long tail for balance.
There are other traits that are associated with arboreal quadrupedalism, but they're really difficult to see online. Another type of quadrupedalism is
terrestrial quadrupedalism. And terrestrial quadrupeds have a lot of the same traits as arboreal quadrupeds because they originally started in the trees. They spend a lot of time on the ground, and they usually go up in the trees to sleep at night or to get food, but they're primarily like socializing and mating on the ground.
So terrestrial quadrupeds, just like the arboreal quadrupeds, have arms and legs of near equal proportion. But the difference between the arms and legs of terrestrial quadrupeds versus arboreal quadrupeds is that terrestrial quadrupeds have longer arms and legs. So although their proportion is equal, right, their lengths are equal to each other, overall the legs and arms are longer than that of the arboreal monkeys. Another difference is that
they have a shorter tail. And so if you look at this tail, this is really short. This is a baboon skeleton, and the tail is super short. There is still a tail because, look, it extends past
the pelvic girdle.
But they don't really need to balance as often as do the arboreal quadrupeds. Remember, arboreal means trees. All right, so now let's move on to knuckle walking. And knuckle walking is something that apes do. So when you see a knuckle walker, you see longer arms and legs right here. And you don't see tails. We don't have any knuckle walkers that are not apes.
Knuckle walkers also have incredibly large and robust proximal phalanges that are flexed because they need to support that very large upper body just by those knuckles. And so this is going to be a key indicator that you're looking at a knuckle walker, the robust proximal phalanges, because all of the apes have longer arms and legs. So a better indicator of knuckle walking are these robust proximal phalanges.
So another type of quadrupedalism is fist walking. The only primate that does fist walking is orangutans, and they don't do it very often because they're mostly in the trees.
So how you can identify when an ape is fist walker or not is by looking at the proximal phalanges. As you can see, these are not as thick and robust as knuckle walkers. But also, the phalanges of the fist walkers are very, very curved in comparison to all other apes, with the exception of the most curved, which is of the gibbon.
Now we're getting into the suspensory primates. One type is the true brachiators, And these are the gibbons and the siamons. And I'll be showing you a clip about these in just a minute. Brachiating means you're swinging in the trees with your arms. So those are the lesser apes, the true brachiators. So the gibbons and the siamons, Hylobaetidae. And then you've got the semi-brachiators, which are those who have a prehensile tail. And then the last is the suspensory climbers. And these are really cool. So these are the longest arms in the primate order. And they have
really thin and delicate looking phalanges. And their thumbs are actually quite short in comparison to the rest of their fingers, but their fingers are incredibly curved and incredibly long, of course, with the exception of the thumb.
When they're standing bipedally, their arms like go all the way down to their feet versus where do our arms go? Like mid-thigh, right? Okay, so this is our example of the true brachiators.
This is Samar. He's 8 years old and lives with his parents and younger sister in a tight family unit. Gibbons are typically monogamous, and his parents have been together for many years. Samar's 1-month-old little sister, Raya. She still needs a lot of looking after. As a baby, she's even paler in color. Her fur won't get its true adult coloring for another 5 years. The family takes a well-traveled trail through the forest. They follow each other in single file. Mom, carrying Raya, pursues Dad, with Samar bringing up the rear. Moving through the forest canopy requires incredible skill and dexterity. Samar's father is a real expert. His swinging motion is a technique known as brachiation. Gibbons have evolved long, strong forearms. Highly mobile joints in their shoulders and wrists enhance their fluid movement. They can reach speeds of 35 miles per hour and cover nearly 30 feet between trees. These graceful gibbons are the true specialists of the canopy. But Samar needs a bit more practice. Close one. For gibbons, the occasional fall is part of life. The important thing is to catch another branch and keep on swinging.
So this is what the gibbon looks like when they're walking bipedally. Quite silly. Okay, so now we'll move on to the next suspensory.
These are the suspensory semi-brachiators. They have the prehensile tail, and so these are New World monkeys. And they use it to move through the trees, and it's thought of as a dietary adaptation because they're often using it to free their hands as they're hanging in the trees to pick fruit, for example. And then they have similar characteristics to arboreal quadrupeds in many ways, but they lack some of the characteristics of true brachiators, like the incredibly long arms. They have equal lengths of arms and legs. The spider monkeys have nubs for thumbs on their hands rather than full opposability. And this is the only primate in the whole primate order that lacks a true opposable thumb for their hands. And that's because they rely on their tails. So they kind of didn't use their thumbs, and over time it went away.
So now here's the clip.
They don't look like a regular primate that has 4 limbs. They have an additional limb that is their tail. So they really look as like spiders when you look at them in the canopy. Spider monkeys are one of the largest primates in the Americas. They can weigh up to 10 kilos, and they are quite amazing because when you look at them, and probably that's why they get their name, they look like spiders. Prehensile tail is a tail that can be used to grab from any substrate. It is like having an additional hand, literally, but only that with a single finger. In fact, they have like a bearskin pad on the underparts of the tail, but it has a very, very detailed precision in order to grab from any kind of substrate. Spider monkeys start using their prehensile tails very early. In fact, after a couple weeks old, baby spider monkeys will start to ride on their mom's back. And it's very interesting that they wrap their tails around their mom's tail, and this is like a seat belt, like a security belt that they have for hanging tight to their mothers. I think prehensile tail is a very unique adaptation because monkeys that have a prehensile tail are able to hang from their tail while they're foraging and then free their hands in order to be more efficient. They can also hang from their tails while wrestling and playing with other members of the group. But especially when they're moving along or across the canopy, they're able to secure themselves while jumping from one tree to another. So it's an additional security for them, especially being large-bodied primates that live 30 to 50 meters above the ground.
So here are the primates who are the slow climbers. So they have really long upper limbs, these slow climbers, even though we see that most of these are strepsirrhines, right? This is a slow loris. This is a potto. These are all strepsirrhines right here. The orangutan is the other slow climber, and they're not always slow. They can be fast, but they are categorized as a slow climber because they use all of their hands as the same. So for example, we use the term quadrumanous to describe orangutans because their feet are not distinguished between their hands when they're moving around in the trees. Okay, let me show you the clip of the orangutans.
The orangutan, the man of the forest. This great ape lives only in Borneo and here in Sumatra. 20,000 years ago it was found on the mainland too, but now these islands are its last refuge. Orangutans are fruit eaters, but prolific fruiting trees like figs are widely scattered, so they have to cover a lot of forest to find enough food. Few trees have enough fruit to feed more than 1 or 2 animals as big as this, so these apes can't live in large groups. Young animals stay with their mothers for several years, but full-grown males are solitary. Despite their weight, orangutans in Sumatra spend most of their time up in the trees. They travel on the ground only when there is no alternative. And this is one reason why. Sumatra still has tigers. A tiger could kill an orangutan, especially a young one.
Orangutans use their body weight to swing through the canopy, but for the youngsters this is a bit of a challenge. They simply aren't heavy enough. Fortunately, Mom is always close by to help out, using her body to form bridges between trees.
Terus ke apa? Itu turun, jalan lagi masuk bangu-bangu, orang bawa parang.
Aspal tu
Tali, apa ni? Tali. So you can make a video sometime nice.
Yeah, I made a video, yeah.
Make a movie.
So notice in this clip how the orangutans use all of their hands and feet the same way. Still, though, the arms are longer than the legs, but they really use their feet the same way as they do their hands, and that's what's called quadrumanous.
So last but not least, we have the bipeds. And when we talk about bipedalism, we know that other primates are capable of walking bipedally. We even saw the lemur, walk in a certain way bipedally, and the gibbon. And we've seen bonobos walk bipedally, and we know that orangutans can do it, but they don't do it habitually, meaning they don't use that for their primary locomotion. The only primate left that does is you and me, so humans. We have anatomical characteristics that enable us to do so, which are the longer legs than arms. However, as you'll see when we get to hominins, there were many, many different species of bipeds that actually had shorter legs than arms. And these are the bipeds that were still adapted to life in the trees, but became adapted to life on the ground. So just know that when we get to human evolution, you don't always have to have longer legs and arms to be a biped. But when we're talking about, the differences between locomotive practices today among living primates, that's what we see. And our foramen magnum is placed
Anteriorly, which means more towards the face. It's under the skull, more towards the face.
In addition, our pelvis is differently shaped. We have a short, broad, bowl-shaped pelvis, and quadrupeds have more of a long, narrow pelvis. And then we also have an S-curve shaped spine instead of one overarching spine. Today, all hominins have a convergent big toe, which means that their toe is non-opposable. So if you look at your own toe, no matter if you can pick up a pen with your toe, it's still not opposable. But all the other primates have opposability in their toe. So that makes us different. We also have an arch, a double arch in our foot. You can see it if you feel your own foot. In addition, you have a really chunky heel bone for shock absorption and short and straight toes. So these are the characteristics of the human foot.